The universe is expanding, but what is it expanding into? This simple question cracks open the deepest mysteries of reality. It challenges everything we think we know about space, boundaries, and existence itself. By the end of this journey, you will understand why this cosmic puzzle is so difficult to solve and explore the most compelling answers science can offer. We will venture from the discovery of the expanding cosmos to the strange force accelerating it, and even peer into theories of a hidden multiverse. We are about to stretch the limits of your imagination. What does an edge of the universe even look like to you? Our story begins not with a telescope, but with a color. For centuries, the universe was seen as a grand, unchanging stage where stars and galaxies played out their eternal roles. Then, in the early 20th century, astronomers like Vesto Slipher began noticing something peculiar. When they analyzed the light from distant spiral nebulae, which we now know are other galaxies, the light was not the color it should be. It was stretched, shifted toward the red end of the spectrum. This redshift was a fingerprint of motion, a cosmic Doppler effect. Just as the pitch of a siren drops as an ambulance speeds away from you, the light from these galaxies was stretched to longer, redder wavelengths because they were racing away from Earth. But one man connected the dots and changed our cosmic story forever. Edwin Hubble, working with the powerful Hooker telescope at Mount Wilson, made two critical measurements. He not only confirmed the redshift of galaxies, he also painstakingly measured their distances. In 1929, he plotted his data and saw a stunning, simple relationship. The farther away a galaxy was, the greater its redshift, meaning the faster it was speeding away. This was Hubble's law, and its message was revolutionary. The universe was not static. It was expanding, with every galaxy rushing away from every other, as if the very fabric of space itself was stretching. Think of a raisin cake baking in an oven. As the dough expands, every raisin moves away from every other raisin. From any raisin's perspective, all the others are receding. We are not at the center of this expansion. We are simply one raisin among countless others, witnessing the same universal stretch. This idea was so radical that it faced fierce resistance. Hubble himself was cautious, and the great Albert Einstein initially rejected the notion, having earlier inserted a fudge factor into his equations of gravity to keep the universe static. Yet the evidence was on the wall, or rather on the photographic plates. It built upon the theoretical work of a Belgian priest and physicist, Georges Lemaitre, who had 2 years earlier proposed a universe born from a primeval atom and expanding. The data forced a monumental shift. The cosmos had a history, a beginning, and a dynamic future. This single observation became the bedrock of modern cosmology, the first solid clue that our universe is an event, not just a place. And with that clue came the next, even more bewildering question. If space is stretching, what exactly is it stretching into? This discovery of an expanding universe demands a new way of seeing space. To grasp what is truly happening, we need to abandon our everyday intuition about how things move. The best tool for this is a simple, classic thought experiment involving a balloon. Picture a perfectly round balloon, not yet inflated, with several small dots drawn on its surface with a marker. These dots represent galaxies. Now begin to blow air into the balloon. As it inflates, what happens to the dots? They all move away from each other. A dot on one side sees every other dot receding. Crucially, no dot is the center of this expansion. From the perspective of any single dot, it appears stationary while all the others are moving away. This is the heart of Hubble's discovery. The galaxies are not racing through space like rockets through the sky. Instead, the space between them, the very fabric of the balloon's surface, is stretching. This is why a more distant galaxy moves away faster. On the balloon, two dots that start farther apart have more stretching rubber between them, so the gap widens at a greater speed with each breath. Now, here is the critical twist that leads directly to our core mystery. In this analogy, we, as observers, are not outside the balloon looking in. We are one of the dots. We are embedded within the stretching fabric. Our entire reality, everything we can see and measure, is confined to that two-dimensional surface. So when we ask what the universe is expanding into, we are asking a question that, from our dot's perspective, may have no meaning. We are asking what lies outside the balloon's surface, a direction that does not exist within our dimensional reality. This is the profound shift in thinking. The expansion is not an explosion into a pre-existing void. It is the creation of more space itself, everywhere, all at once. This balloon analogy reveals the true nature of our cosmic dilemma. Our language betrays us. When we say the universe is expanding, our brains immediately picture an ordinary object, like a cloud of smoke or an inflating beach ball. These things expand into the surrounding air, pushing it aside. They have an edge, a boundary between what is the object and what is not. This is how everything in our daily experience works. We instinctively apply this logic to the cosmos. We picture the galaxies flying outward through some vast, empty container, and we wonder what's on the other side of the final galaxy. But that picture is wrong. The universe is not an object in space. The universe is space and time, and all the matter and energy within it. It is the container itself. So when cosmologists say the universe is expanding, they mean the container is getting bigger. The very grid of reality, the stage upon which everything plays out, is stretching. This leads to a mind-bending conclusion. If the universe is all of space, then there is no outside for it to expand into. By definition, outside would just be more space, which would then be part of the universe. The question, what is it expanding into, assumes there is a something beyond the everything, a place for the everything to go. But if the universe is truly everything that exists, then that place does not exist. It is not a blank, empty void waiting to be filled. It is a literal nothingness, a complete absence of dimensions, time, and physical laws. It is not just empty space, it is no space at all. This is the first major conceptual hurdle. We are trying to visualize a process that has no analog in our three-dimensional world. We are dots on a balloon, trying to point a finger in a direction that does not exist on our surface. The expansion we measure is not a movement through space, but the relentless creation of new space between every point. Every second, the distance between distant galaxies grows not because they are flying apart, but because the cosmic fabric between them is continuously weaving itself larger. So the most straightforward answer to our original question is also the most difficult to accept. The universe isn't expanding into anything because there is no into. There is just more universe. This leads us to a crucial distinction, one that defines the very limits of our cosmic vision. Even if the universe is infinite, what we can ever know of it is not. We live inside a bubble of information, a sphere called the observable universe. Its boundary is not a physical wall, but a horizon in time. Light has a speed limit, the fastest anything can travel through space. In the 13.8 billion years since the Big Bang, light from the most distant objects has been racing toward us. The observable universe is simply the region of space from which that light has finally had time to arrive at our telescopes. Think of standing in a vast, foggy field at night, holding a lantern. You can only see as far as the light from your lantern has traveled and reflected back. The cosmos is similar, but the lantern was lit 13.8 billion years ago, and we are only now seeing the glow from the most distant edges of that illuminated sphere. The staggering result is a bubble nearly 93 billion light-years across. That number is much larger than 13.8 billion because space itself has been stretching during the entire journey of that ancient light, dramatically increasing the distance the light had to cover. This cosmic horizon is our ultimate limit. We cannot see, detect, or interact with anything beyond it because light from those regions has not had enough time to reach us. It is entirely possible, even likely, that the universe extends far, far beyond this horizon, perhaps forever. But for us, it is a permanent veil. Every galaxy, every star we will ever observe exists within this bubble. The rest is hidden, a realm of pure speculation. So when we ask what the universe is expanding into, we must confront a humbling truth. We are not even equipped to see the entirety of the universe, let alone what might lie beyond its ultimate edges. Our entire reality is confined to this observable sphere, and its expansion is the only expansion we can ever measure. Our cosmic horizon presents a profound question about the nature of reality itself. Is the universe we inhabit in its totality finite or infinite? This is not a question of what we can see, but of the ultimate architecture of all that exists. The answer depends on the shape of space, a concept far stranger than it sounds. We are used to things being flat, like a sheet of paper, or curved, like the surface of a ball. But the universe has a geometry in 3 dimensions, and its shape dictates whether it is an endless expanse or a closed, finite cosmos. One compelling possibility is a finite universe without any edge or boundary. To visualize this, we must return to our balloon analogy, but with a crucial upgrade. The surface of the balloon is a 2-dimensional sphere. If you were a tiny ant living on that surface, you could walk forever in a straight line and never find an edge. Yet the surface itself has a finite area. If you traveled far enough, you would eventually circle the entire sphere and return to your starting point. Now imagine this same principle applied to our 3-dimensional universe. This shape is called a 3-sphere. In a finite, closed universe of this type, space curves back on itself in a higher dimension we cannot perceive. A spaceship traveling in a perfectly straight line for an unimaginably long time would not reach a cosmic wall. Instead, it would circumnavigate the entire cosmos and arrive back home from the opposite direction. There would be no boundary, no outside, just a finite volume of space that is perfectly self-contained. The other possibility is an infinite, flat universe. In this model, space does not curve back on itself. It extends forever in every direction, an endless sea of galaxies and emptiness with no loop, no return journey, and no end. This is the more intuitive, yet also more dizzying concept. Infinity is not just a very big number. It is a totality that never stops. In an infinite universe, every possible arrangement of matter, every variation of you reading this script would exist somewhere in the vastness. So which one is our reality? Scientists use the cosmic microwave background, the afterglow of the Big Bang, as a cosmic ruler to measure the geometry of space. The patterns in this ancient light tell us about the universe's curvature. After decades of precise measurements from satellites like WMAP and Planck, the data points overwhelmingly to a flat universe. The curvature is so minute, if it exists at all, that it is beyond our ability to detect. A flat geometry within our observable bubble strongly suggests an infinite universe. But here is the critical caveat. We can only measure the curvature within our observable horizon. It is possible the universe is like a vast, gently curved saddle, which would be infinite, or a gigantic sphere so large its curvature is imperceptible to us, like the Earth feeling flat from your backyard. Our instruments may simply be unable to see the bend in the cosmic fabric over such immense scales. So while the evidence leans heavily toward a flat and likely infinite cosmos, we cannot say for certain. We are trapped within our sphere of observation, trying to deduce the shape of a room whose walls we can never touch. This uncertainty lies at the very heart of our mystery. If the universe is infinite, then it was already infinite at the moment of the Big Bang. The expansion is not stretching a finite object into infinity, but stretching an infinite grid, making the distance between every point grow larger. The idea is almost impossible to fully grasp. How can you expand something that is already without end? the shape of the universe is just the beginning of the story. To truly grasp how space can stretch, we must understand the very material it is made from. That material is not a substance you can touch, but a concept that forever changed physics, spacetime. This idea was the brilliant, revolutionary core of Albert Einstein's theory of general relativity. Before Einstein, space was seen as a static, empty stage, and time as a universal clock ticking independently in the background. General relativity wove them together into a single, dynamic fabric. Picture a vast, taut rubber sheet. This sheet represents the four-dimensional fabric of spacetime. Now place a heavy bowling ball in its center. The ball sinks, creating a deep well or curvature in the sheet. This is how mass and energy interact with spacetime. A planet or a star does not simply sit in space. It warps the very fabric around it, and this warping is what we feel as gravity. A marble rolled near the bowling ball will spiral inward, not because of a mysterious force pulling it, but because it is following the curved path, the downhill slope created by the heavy object. The Earth orbits the Sun because it is rolling around the deep curve the Sun makes in the cosmic fabric. This is gravity reimagined not as a force but as geometry. The rubber sheet analogy shows us that spacetime is not rigid. It is flexible, dynamic, and responsive. It can be curved, dented, and even rippled, as we have now detected with gravitational waves from colliding black holes. But on the grandest scale of all, across billions of light years, a different phenomenon dominates. Instead of being curved by concentrated masses, the entire fabric is undergoing a steady, relentless stretch. Think back to the balloon, but now imagine the rubber itself is the fabric of spacetime. The galaxies are not moving through it, they are essentially pinned to it. As the balloon inflates, the rubber stretches, and the distance between every pin increases. This is the expansion of the universe described by the equations of general relativity. The theory provided the perfect language for this cosmic growth. Yet, when Einstein first applied his equations to the whole cosmos, he was disturbed. They predicted a universe that must either be expanding or contracting. Believing the universe to be eternal and static, he added a fudge factor, a cosmological constant, to hold the fabric still. A decade later, when Edwin Hubble showed the universe was indeed expanding, Einstein called this constant his greatest blunder. But the story of the cosmological constant was far from over, because the stretch of spacetime held another, more shocking secret. The expansion was not slowing down as everyone expected. It was speeding up. Einstein's so-called blunder was about to make a dramatic comeback. For most of the 20th century, astronomers assumed the expansion of the universe was a cosmic sigh, a gradual slowing down from the explosive force of the Big Bang. The mutual gravitational pull of all the matter in the cosmos, it was thought, was acting like a brake, gently tugging on the fabric of spacetime to decelerate the stretch. The big question was whether there was enough matter to one day halt the expansion entirely and pull everything back in a big crunch, or if it would just coast forever, slowing to a near standstill. To settle this, two independent teams of astronomers in the late 1990s set out to measure the expansion rate over cosmic time by observing incredibly distant stellar explosions called Type 1, a supernova. These supernovae act as standard candles, their known intrinsic brightness allowing scientists to gauge their distance with precision, while their redshift reveals how fast the universe was expanding when their light was emitted billions of years ago. The results were not just surprising, they were universe-shattering. The data from the most distant supernova showed they were fainter and therefore farther away than expected. This could mean only one astonishing thing: the expansion of the universe was not slowing down. It was speeding up. Some mysterious repulsive force was overpowering the collective gravity of all galaxies, clusters, and dark matter, pushing space apart faster and faster. This discovery earned the teams the Nobel Prize and forced cosmology into a new paradigm. the unknown driver of this accelerating expansion was given a name that echoed our ignorance: dark energy. To explain this bizarre effect, physicists revived Einstein's discarded cosmological constant, reinterpreting it not as a fix for a static universe, but as a fundamental property of empty space itself. Imagine the vacuum of space is not truly empty. According to quantum physics, it is a seething, bubbling foam where virtual particles flicker in and out of existence. This quantum foam is thought to possess a baseline energy, an intrinsic tension woven into the fabric of spacetime. This is the essence of dark energy. It is not a force that pushes from one place to another. It is a property of space, and here is the critical, mind-bending part. The more space there is, the more dark energy there is. As the universe expands, it creates new space. That new space contains its own dark energy, which adds to the repulsive effect, causing the expansion to accelerate further, which creates even more space and more dark energy. It is a runaway, self-reinforcing cycle. Dark energy behaves as a kind of anti-gravity, but it does not attract or repel objects. It stretches the stage on which they sit. Think of our inflating balloon again, but now imagine the rubber has a strange, built-in springiness. The more it stretches, the more powerfully it wants to stretch, as if the fabric itself is actively trying to inflate. This is the engine driving the expansion we measure today. It constitutes about 68% of the total energy content of the cosmos, making it the dominant component of our universe. So when we ask what the universe is expanding into, we are really asking about the behavior of this enigmatic dark energy. It is the unseen hand relentlessly stretching the cosmic canvas, and its ultimate nature remains one of the greatest mysteries in all of science. This accelerating expansion, driven by dark energy, forces us to look back to the very beginning. To understand where the universe is going, we must confront a fundamental error in how we picture its birth. The term Big Bang itself is a misnomer, conjuring an image of a cosmic firecracker detonating at some location in a vast, empty void. That picture is completely wrong. The Big Bang was not an explosion in space. It was the explosive emergence of space itself. Think back to our inflating balloon, the entire surface representing all of space. The Big Bang is not a firework going off on one part of the balloon. It is the moment you begin inflating it from a state of being unimaginably tiny and dense. At that initial moment, every single point on the balloon's entire surface, every location that would one day become a galaxy or a void, was compressed together. There was no outside of the balloon, no empty room it was sitting in. The balloon, the fabric of reality, was all there was. This means there is no center to the expansion and no edge from which it exploded outward. From our perspective as a dot on the balloon, we see all other dots moving away, making it seem like we are at the center. But a dot on the opposite side sees exactly the same thing. Every point in the universe has this same centerless view. The cosmic microwave background radiation, that ancient afterglow from the hot early universe, confirms this perfectly. It reaches us with near uniform intensity from every direction in the sky. The heat of creation is not coming from one specific point we can point to. It is coming from everywhere because we are inside the expanding remnant of that event. So what was the Big Bang if not an explosion into nothingness? It was the rapid expansion of spacetime from a state of extreme density and temperature. All the energy that would become galaxies, stars, and us was contained within that hot, dense beginning. There was no pre-existing emptiness for it to fill. The expansion created the emptiness as it went, weaving new space into existence between the particles of the primordial fire. Asking what happened before the Big Bang, or what it expanded into, may be like asking what is north of the North Pole. Our concepts of before and outside are tied to time and space, and according to our best models, time and space as we know them began at that moment. The question itself might lose its meaning at that frontier. we are left with a universe that is not an object in a container, but is the container, and the container has been stretching and accelerating its own stretch since the very first moment. Dark energy's relentless push forces us to consider the ultimate fate of our cosmic canvas. But what if our universe is not the only canvas? When the question of what it expands into becomes too confining, one radical answer emerges. Perhaps it expands into a realm of other universes, a cosmic ocean where our cosmos is just one bubble among an infinite froth. This is the multiverse hypothesis. It is not a single theory, but a family of ideas born from the edges of cosmology and quantum physics. One of the most compelling versions arises directly from our story of cosmic inflation, the theory that the universe underwent a period of unimaginably fast expansion just after the Big Bang. The concept of eternal inflation suggests that this inflationary process never truly stopped everywhere. Instead, it is a perpetual state of a larger background reality. Picture a vast, bubbling pot of water coming to a boil. Our universe is like a single steam bubble that formed, inflated rapidly, and then settled into the slower, steadier expansion we see today. But the boiling pot itself, the seething, high-energy background, is eternal inflation. In that roiling foam, new bubbles are constantly nucleating, each one a new universe with its own Big Bang, inflating into its own isolated domain. In this view, our universe is not expanding into nothingness. It is expanding into this larger, pre-existing spacetime foam, the megaverse. The boundary of our bubble universe would be a wall of incredible energy, a domain where the inflation that birthed us finally decayed. Beyond that wall lies the inflating background and countless other bubbles, each potentially with its own unique set of physical laws and constants. In some, gravity might be repulsive. In others, atoms might never form. Our universe's particular rules, the fine-tuned constants that allow for stars, planets, and life, would be just one random draw from an infinite cosmic lottery. This idea is a breathtaking extension of cosmology, but it comes with a profound caveat. These other bubble universes would be causally disconnected from ours. No light, no information, no signal could ever cross the gap. The inflating space between bubbles expands faster than light can travel, erecting permanent, impenetrable walls. This makes the multiverse in its current form a philosophical speculation as much as a scientific one. It is a beautiful, mathematically consistent answer to our question, but one that lies, for now, beyond the reach of observation or experiment. We are like fish in a perfectly sealed aquarium, theorizing about an entire ocean outside, but with no way to ever poke a fin beyond the glass. This multiverse of bubbles is not pure fantasy. It emerges from one of the most successful and elegant theories in modern cosmology, the idea of cosmic inflation. To understand it, we must rewind the cosmic clock to a fraction of a second after the Big Bang, to a time when the universe was smaller than a single proton. The standard Big Bang model has puzzles, like why the universe is so uniform in temperature from one side of the sky to the other. Regions that are now billions of light years apart were once close enough to exchange heat, but not nearly close enough in the time available since the beginning. It is as if two cups of coffee placed on opposite sides of a continent instantly reached the same temperature without ever being connected. The theory of inflation, proposed in the 1980s, solves this by suggesting the universe underwent a brief, unimaginably violent growth spurt. For a sliver of time, perhaps around 10 to the power of -36 seconds, the fabric of spacetime expanded faster than the speed of light. Not by objects moving through space, but by space itself inflating at an exponential rate. In that fleeting moment, a region smaller than a subatomic particle was stretched to a size larger than our entire observable universe today. This explains the uniformity. Everything we see was once a tiny, connected patch that was blown up to cosmic scales, smoothing out any wrinkles or temperature differences. It is like taking a tiny, crumpled piece of paper and inflating it to the size of the Earth. The wrinkles become so stretched they are imperceptibly smooth. But the story of inflation holds an even more profound twist. According to quantum physics, empty space is not placid. Even during that explosive inflation, the quantum field driving the expansion would have been subject to tiny, random fluctuations. These are not flaws but features. Imagine the inflating universe as a vast, rising loaf of bread dough. The yeast causes the dough to expand, but tiny air bubbles also form and get stretched within the loaf. Those quantum fluctuations during inflation were like the seeds of those bubbles. As the inflationary field decayed in different places, its immense energy converted into the hot soup of particles of the traditional Big Bang. But here is the key. The theory of eternal inflation suggests that in most of the grand background landscape, this decay never completes. Inflation is a runaway process. Once it starts, it tends to keep going, creating more inflating space exponentially faster than it can decay. But in rare, random patches, the inflationary field does settle down. Each of those patches becomes a separate, isolated bubble universe, like a pocket of calm air forming within a raging hurricane. Our entire cosmos, all 93 billion light-years we can observe, is just one such bubble. We live inside a pocket where inflation stopped 13.8 billion years ago, allowing for stars, galaxies, and us to form. But outside our bubble wall, the grand inflationary landscape likely continues to rage, eternally giving birth to new bubble universes, each with its own random set of physical properties. In this breathtaking picture, the multiverse is not a separate idea. It is a direct, almost inevitable consequence of the mechanism that created our own universe. We are not expanding into a meaningless void. We may be one bubble gently pressing against the walls of our own creation in an infinite, frothing sea of other realities. Yet the idea of an eternal multiverse still leaves a fundamental question hanging in the air. What is the nature of that space between the bubbles? We have replaced one container with another, shifting the question of what is it expanding into to a grander scale. But this forces us to confront the deepest, most elusive concept of all, nothing. If our universe is not expanding into another something, then is it expanding into nothing? The word nothing seems simple, but it is a trap for the mind. In our daily lives, nothing is an empty box, a blank page, a silent room. It is the absence of things within a space that already exists. But when we apply it to the cosmos, we are talking about the absence of space itself. This is not an empty container. It is the absence of the container, the absence of dimensions, of time, of any possibility for something to be absent from. Can such a state even exist? Physics has already shown us that the closest thing to nothing we can describe is not empty at all. Even in a perfect vacuum at the smallest scales, space is not a still, dark void. It is a seething, turbulent quantum foam. According to the rules of quantum mechanics, pairs of virtual particles and antiparticles spontaneously blink into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This is not a metaphor. It is a measurable effect called vacuum fluctuation, with real consequences for how atoms behave. So the nothing of empty space is actually a vibrant, energetic field pregnant with potential. This quantum foam is the stage upon which our universe may have emerged, but this is still a something. It has properties, it obeys laws, it fluctuates. It is a physical state. What about absolute nothingness, the complete and total absence of anything whatsoever? No space, no time, no quantum fields, no laws of physics, not even the potential for them. This is a concept that may lie beyond human comprehension. Our brains are wired to think in terms of objects, relationships, and causes existing within a framework. Imagining the lack of any framework at all is like trying to visualize a color that does not exist. Philosophers and physicists have long debated whether absolute nothingness is even a coherent idea. If we say the universe emerged from nothing, we are implying there was a state of nothingness that somehow transitioned into a state of something. But a transition requires time, and time is a property of something. A cause requires laws, and laws are also something. The very question what was before the Big Bang smuggles in the concept of time, which may have begun with the universe. So perhaps absolute nothingness is not a place or a state that can exist. It is simply the logical negation of existence, a concept we use to define what is by contrasting it with what is not. It is the answer to a question that, when pushed to the ultimate extreme, may cease to have any meaning at all. Asking what the universe expands into may be like asking what sound the color blue makes. We are mixing categories that do not belong together, using the language of containers and movement to describe a reality where those ideas have no purchase. So if the universe is finite, does it have a wall? The idea of a physical boundary is deeply satisfying to our intuition. We imagine traveling for eons, finally reaching the last galaxy, and then peering over a cosmic precipice into what? An endless void, a solid wall of crystalline energy. Science fiction has painted vivid pictures of such edges, yet physicists almost universally dismiss this possibility. A true physical edge creates more problems than it solves. What would that wall be made of? How could it just stop? Most critically, a boundary demands an explanation for what lies on the other side. It immediately resurrects our original, perhaps unanswerable question. If there is a wall, then there is something outside that wall, even if it is just empty space. That something, by definition, would then be part of a larger reality, a bigger container. You have not found the edge of existence, you have just found the edge of your room. The universe, if it is to be truly all-encompassing, cannot have a wall in this familiar sense. It must be self-contained, a reality that needs no outside. This need for a self-contained cosmos led to one of the most elegant proposals in theoretical cosmology, the no-boundary proposal by James Hartle and Stephen Hawking. Their idea was to remove the need for a starting edge, just as we removed the need for an expanding edge. Think about the North Pole on Earth. If you stand at the North Pole and ask which way is north, the question loses meaning. Every direction from that point is south. The North Pole is not a cliff you can fall off. It is a unique coordinate, a point where our usual concept of further north ceases to exist, yet the surface of the Earth continues smoothly. Hartle and Hawking applied a similar logic to the beginning of the universe in time. In their model, if you could run the cosmic film backward toward the Big Bang, time itself would become more and more like a spatial dimension. The sharp, singular point of beginning would smooth out into a rounded, closed geometry, like the tip of a shuttlecock or the rounded bottom of a wine glass. There is no boundary in time, no moment of creation you can point to and say before this there was nothing. Instead, the universe simply is in a self-consistent, finite, yet unbounded way. It has no more of an edge in time than the Earth has an edge at the North Pole. This proposal does not answer what the universe expands into, because it elegantly sidesteps the need for an outside altogether. The cosmos, in this view, is its own complete entity, a finite bubble of reality that requires no external container to make sense. The search for a self-contained cosmos leads us to a startling possibility. What if our universe is not the whole story, but merely a slice of a much grander, higher dimensional reality? This is not science fiction, but a serious proposal arising from the quest to unify all the forces of nature, a theory known as string theory. In its attempt to reconcile gravity with quantum mechanics, string theory requires something extraordinary. It posits that the fundamental particles of the universe are not point-like dots, but unimaginably tiny, vibrating loops of energy, strings, and for the mathematics of these vibrations to produce all the forces and particles we see, they must vibrate in more than just the 3 dimensions of space we know. String theory suggests there are at least 9 or even 10 spatial dimensions. We do not perceive these extra dimensions because they are curled up or compactified at a scale so small, 1 billion times smaller than an atom, that they are hidden from our view. It is as if you were looking at a long, thin garden hose from a great distance. From afar, it appears as a simple one-dimensional line. Only upon incredibly close inspection could you see its circular, two-dimensional surface. Our reality might be like that, a three-dimensional surface in a space of many more dimensions. This idea of hidden dimensions gave rise to a particularly compelling cosmological model called brain world theory. In this picture, our entire universe is not a bubble, but a three-dimensional membrane, or brain for short, floating within a higher dimensional space called the bulk. Think of our cosmos as an enormous, impossibly thin sheet of paper, a page in a book of unimaginable thickness. We are confined to that page. All the matter and forces we know, except for gravity, are like ink stuck to the paper. They cannot leave the surface of our brain. This is why we only experience three spatial dimensions, but gravity, according to this model, is different. It is a force that can leak off our brain and propagate through the higher dimensional bulk. This could explain why gravity is so astonishingly weak compared to the other fundamental forces. Its strength is diluted as it spreads out into these extra dimensions. In a brain world scenario, the expansion of our universe takes on a new and literal meaning. Our three-dimensional brain could be moving, stretching, or even colliding with other brains within the bulk. When we say the universe is expanding, we are not just talking about space stretching within our brain. We could be talking about our entire brain drifting into the higher dimensional bulk, like a soap film expanding on the surface of a pond. So what is our universe expanding into? In this model, it is expanding into the bulk itself. There is an outside, a higher dimensional arena, but it is one we are fundamentally unequipped to perceive directly. We are flatlanders living on a sheet, trying to understand why our sheet is getting larger, while the true explanation lies in movements we cannot point to, in directions that do not exist for us. This provides a concrete, though profoundly strange, answer to our original question. The mystery is not gone, it has simply been elevated to a realm beyond our senses. Yet another radical idea from the edge of physics shatters our notions of inside and outside completely. It is called the holographic principle, and it begins not with the cosmos, but with the most enigmatic objects within it, black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which is a measure of its hidden information or disorder, is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is proportional to the area of its event horizon, the two-dimensional spherical surface that marks its point of no return. This was bizarre. It suggested that all the information about everything that ever fell into the black hole, every atom, every memory, every star, was not lost inside its infinite depth. It was somehow encoded, pixelated, onto the surface of its horizon. The three-dimensional interior was being described by a two-dimensional boundary. This is the essence of a hologram. A standard security hologram on a credit card is a two-dimensional piece of film. But when light shines on it, it projects a full three-dimensional image that you can look around. The holographic principle proposes that our universe might operate in a similar, though far more profound, way. The three-dimensional reality we experience with all its galaxies, stars, and planets might be a projection. The true information describing our cosmos might be encoded on a distant, two-dimensional surface that surrounds us. But what could that surface be? One compelling candidate is the cosmic horizon itself, the ultimate limit of our observable universe. Think of it like this: we are like characters living inside a giant, immersive movie. We experience the story in three dimensions, feeling the depth and the movement all around us. But the entire movie, all the information needed to generate our rich reality, is stored on a flat, two-dimensional reel of film at the boundary of the theater. In this cosmic analogy, the film reel is the spherical shell of our cosmic horizon. Every event, every particle, every bit of the history of our universe within that sphere could be represented by tiny, fundamental bits of information painted onto that inner surface. What we perceive as the expansion of three-dimensional space with galaxies rushing apart might simply be the consequence of information being processed on that evolving two-dimensional screen. The distinction between the inside of the universe and what lies outside it then becomes a profound illusion. If our reality is a holographic projection, then the question of what the universe expands into takes on a completely new character. We are not asking about a container, we are asking about the projector. The three-dimensional universe we measure might be expanding because the two-dimensional information surface that encodes it is changing, growing, or updating in a specific way. The outside is not a place, it is the abstract realm where the information is stored before it is projected into the volume we inhabit. This principle remains a theoretical frontier, a breathtaking possibility that emerges from the clash between quantum mechanics and gravity. It has not been proven, but it is taken seriously because it solves deep paradoxes about information and black holes. It suggests that the deepest nature of reality might not be what it seems. We may be living in a shadow, a magnificent and convincing projection whose source code is written on the farthest wall we can never touch. The most powerful evidence for this cosmic story is not found in distant galaxies, but in the faint, cold glow that fills every cubic inch of the space around us. This is the cosmic microwave background radiation, the oldest light in the universe. It is the afterglow of creation itself, cooled and stretched by 13.8 billion years of relentless expansion. To understand it, picture the universe in its fiery infancy, a mere 380,000 years after the Big Bang. Before that moment, the cosmos was an opaque, searing plasma, so dense that light particles, photons, could not travel freely. They were constantly bouncing off a thick fog of free electrons and protons, like headlights in a dense, blinding blizzard. Then, as the universe expanded and cooled, a pivotal event occurred. The temperature dropped enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, the fog lifted. The photons which had been trapped were finally set free. That first flash of clear light has been traveling through the expanding universe ever since. We are bathed in that ancient light right now, but the expansion of space has done something profound to it. As the fabric of the cosmos stretched, the wavelengths of that primordial light stretched along with it. The incredibly energetic, short wavelength light from the hot early universe has been redshifted all the way down into the microwave part of the spectrum. This is why we detect it today not as visible light, but as a uniform, cold whisper of microwave radiation, just a few degrees above absolute zero. It is the ultimate fossil, a baby picture of the cosmos. Its discovery in 1965 by Arno Penzias and Robert Wilson was a triumphant, accidental confirmation of the Big Bang model, silencing rival theories of a steady-state universe. But the story of the cosmic microwave background did not end there. Its true power lies in its minute imperfections. While the glow is remarkably uniform, it is not perfectly smooth. Detailed maps from satellites like COBE, WMAP, and Planck have revealed a faint speckled pattern, tiny variations in temperature, mere millionths of a degree. These are the cosmic seeds. Those tiny fluctuations in density are the imprints of the quantum foam from the universe's first moments, stretched to cosmic scales by inflation. They are the gravitational blueprints for everything that would follow. The slightly denser patches, revealed by slightly warmer spots in the microwave sky, held just enough extra gravitational pull to eventually attract more matter. Over billions of years, these seeds grew into the vast cosmic web we see today, the clusters and superclusters of galaxies separated by immense voids. By studying the precise statistical patterns in this speckled map, Cosmologists can read the universe's vital signs. The size and distribution of the hot and cold spots tell us the universe is geometrically flat, supporting the idea of an infinite cosmos. They precisely measure the amounts of ordinary matter, and dark energy. They confirm the predicted age of the universe. This faint microwave hiss is not just a relic. It is a detailed cosmic ledger, a data-rich message from the dawn of time that grounds our most sweeping theories in hard, observable evidence. It tells us the expansion is real. It traces that expansion back to a hot, dense beginning, and it shows us the very structures that grew because of it. The cosmic microwave background tells us where we came from, but dark energy dictates where we are going. This relentless acceleration points toward a specific and profoundly bleak ultimate fate for the cosmos, often called the Big Freeze or heat death. It is the logical conclusion of an expansion that never stops and even speeds up forever. Picture our observable universe today, a bustling metropolis of galaxies. Now fast forward billions of years, because space itself is stretching at an accelerating rate. Distant galaxies will not just move away, they will eventually vanish. Their light, stretched to longer and longer wavelengths, will fade into invisibility. Then, the expansion will push them beyond our cosmic horizon altogether, their light unable to ever reach us again. From the perspective of any surviving civilization, the universe will appear to shrink. Galaxy after galaxy will wink out of the sky, not from going dark, but from being carried away by the stretching fabric of space faster than their final photons can chase us down. Our local group of galaxies, bound together by gravity, may remain as a single, isolated island in an ever-growing sea of emptiness, but even this island has an expiration date. All the stars over trillions of years will eventually exhaust their nuclear fuel. Some will explode, others will fade to cold, dark embers called black dwarfs. The universe will grow darker and colder with each passing eon. This is the essence of the heat death. It is not a dramatic explosion or a collapse. It is a slow, quiet fade to black, driven by the relentless increase of entropy, which is a measure of disorder. In any closed system, things tend from order to disorder. A hot cup of coffee cools to room temperature. A neat stack of papers scatters. The universe is the ultimate closed system. All the energy that once powered stars and galaxies will become uniformly spread out across an unimaginably vast volume. With no temperature differences, no hot spots or cold spots, no usable energy gradients can exist. It will be a state of perfect, featureless equilibrium. A cosmos where every place is the same as every other place, a few degrees above absolute zero, populated only by the ghostly remnants of dead stars and planets drifting infinitely far apart. The expansion itself becomes the engine of this eternal winter. By creating more and more space, it ensures that the universe's energy becomes so dilute that it can never again coalesce to spark new stars or new beginnings. The Big Freeze is the ultimate victory of emptiness over structure, of stillness over activity. It is a future of profound silence and darkness, underscoring the irreversible, one-way nature of the cosmic expansion we witness today. This fate is not certain, but it is the leading forecast based on our current understanding of dark energy. It paints the expansion not as a simple fact, but as the defining narrative of cosmic history, a story with a beginning, a middle, and a very cold, very distant end. Yet the Big Freeze is not the only possible end to this cosmic story. Dark energy, the mysterious force driving our acceleration, could have a much more violent destiny in store. This alternative is known as the Big Rip. In the Big Freeze, dark energy stretches space so fast that structures are pulled apart over eons, but the fundamental forces holding atoms together ultimately win. The Big Rip imagines a far more potent form of dark energy, one that grows stronger over time. If this phantom energy, as it is sometimes called, increases in density, its repulsive power would become infinite. The stretching of space would not just accelerate, it would skyrocket. First, the force would overcome the gravity binding galaxy clusters together, flinging them into the void. Then, as the rip intensified, it would tear apart individual galaxies. Solar systems would be shredded. The relentless stretching would then overcome the forces holding stars and planets together. In the final, horrific moments before time itself ends, the fabric of space would stretch faster than the speed of light at a local level. The phantom energy would overcome the electromagnetic force holding molecules together, and then the strong nuclear force binding atomic nuclei. In a final flash, every atom, every proton and neutron would be torn asunder. Reality would dissolve into a mist of disconnected fundamental particles, each alone in an infinitely stretched void, unable to ever interact again. The universe would end not with a cold whimper, but with a catastrophic, instantaneous shredding of spacetime itself. This scenario is a stark reminder that the nature of dark energy, still unknown, holds the key to our ultimate fate. Currently, our measurements of dark energy are consistent with it being a constant force, a property of space itself, which leads to the Big Freeze, but we cannot yet rule out the possibility that it evolves, setting a countdown to a much more dramatic finale. This violent possibility stands in direct opposition to an older, once dominant vision of the end, the Big Crunch. For much of the 20th century, scientists debated whether the universe contained enough matter for gravity to one day halt the expansion. If the density of the cosmos was above a critical threshold, the collective gravitational pull of all galaxies would act as a cosmic brake, slowly reversing the outward flight. The expansion would slow, stop, and then begin to run in reverse. Galaxies would begin rushing toward each other. The background temperature of space, now near absolute zero, would begin to rise as the cosmic microwave background radiation is blue-shifted back into higher energies. The universe would heat up as it contracted. Eventually, clusters and galaxies would collide and merge in a fiery chaos. Space itself would shrink, cramming all matter and energy into an ever smaller, ever hotter volume. The final act would be the mirror image of the Big Bang, a catastrophic collapse into a singularity of infinite density, a point where the laws of physics break down. Some theories even suggested this singularity could trigger another Big Bang, leading to a cyclic universe of endless expansion and contraction, a cosmic heartbeat across eternity. The Big Crunch offered a kind of poetic symmetry, a return to the origin. It was a compelling narrative, but it relied on a dense universe. Our most precise observations have delivered a verdict. The combined density of ordinary matter and dark matter is not nearly enough to halt the expansion. Furthermore, the discovery of accelerating expansion was the final, definitive blow. Gravity is not pulling the universe back together. Dark energy is pushing it apart, and with increasing vigor. The data from supernova, the cosmic microwave background, and large-scale galaxy surveys all converge on the same conclusion. The Big Crunch is off the table. The universe is not destined to collapse. It is fated to expand, and expand faster forever. For now, the evidence strongly points away from the dramatic symmetry of a crunch or the terrifying violence of a rip, and toward the long, slow, cold dissolution of the Big Freeze. Our cosmos appears set on a path of quiet, irreversible dispersion, where the story of structure and complexity gradually fades into an eternal, uniform stillness. The geometry of the cosmos is not just an abstract mathematical idea. It is the ultimate blueprint determining whether the universe is finite or infinite and what its final fate will be. This geometry hinges on a single critical number, the density of the universe. Imagine the total amount of matter and energy in the cosmos, averaged out across the vastness of space. Scientists compare this actual density to a theoretical critical density, a perfect balance point. The ratio between these two values dictates the shape of space itself, and there are only three possibilities. The first is a flat universe. This occurs when the actual density exactly equals the critical density. In this geometry, parallel lines stay parallel forever, and the angles of a triangle add up to exactly 180 degrees, just like on a flat sheet of paper. A flat universe has zero overall curvature. Most importantly, if it is flat, it is almost certainly infinite in extent. The expansion would continue forever, gradually slowing toward a stop but never reversing. The second possibility is an open universe. Here, the actual density is less than the critical density. There is simply not enough matter and energy to curve space back on itself. The geometry is negatively curved like a saddle or the surface of a Pringles chip. In this shape, parallel lines diverge, and the angles of a triangle add up to less than 180 degrees. An open universe is also infinite, and its expansion would continue forever, with gravity never being strong enough to pull everything back together. The third and most intuitively satisfying shape is a closed universe. This happens when the actual density is greater than the critical density. Space has positive curvature like the surface of a sphere. On a sphere, parallel lines eventually meet, and a triangle's angles add up to more than 180 degrees. A closed universe is finite in volume with no edges. If you traveled far enough in a straight line, you would circumnavigate the entire cosmos. In this model, the expansion could eventually be overcome by gravity, leading to a big crunch. For decades, cosmologists searched for this curvature, this bend in the fabric of reality. The quest was answered by the most ancient light we can see. The Planck satellite, mapping the cosmic microwave background with exquisite precision, looked for telltale signs of warping in the patterns of the primordial glow. The data delivered a clear verdict. The universe is flat to an astonishing degree of accuracy. The observable cosmos shows no measurable curvature. This powerful evidence points toward a flat geometry, which strongly suggests our universe is infinite. We are not living on the surface of a colossal, unseen sphere. We are likely part of an endless expanse, a grid stretching forever in every direction, with the strange implication that it was already infinite at the moment of the Big Bang. The expansion we see is not an object growing into emptiness, but an infinite grid itself stretching, creating more of itself between every point. This flat, likely infinite geometry brings us face to face with a profound paradox. Our language, the very tool we use to frame the question, is fundamentally mismatched to the cosmos. Words like outside, into, and expand are born from a world of objects and containers. They work perfectly for a balloon inflating in a room or a plant growing in a garden. But when we apply them to all of reality, they strain, crack, and finally break. Asking what the universe expands into may be a category error. It is like asking what sound the color blue makes or what lies north of the North Pole. At the North Pole, every direction is south. The concept of further north simply ceases to have any meaning at that specific point. In a similar way, if the universe is truly all that exists, the totality of space, time, matter, and energy, then the concept of an outside ceases to have any meaning. There is no there. It is not a blank void waiting to be filled. A void is still a volume, a something. We are trying to conceive of a literal nothingness, an absence of dimensions, laws, and even the potential for existence. Our brains, honed by millions of years of evolution in a local, three-dimensional environment, are not wired to process this. We are like ants living on a vast, flat leaf, trying to understand the concept of up. The ant can perceive forward, backward, left, and right, but the third dimension is utterly outside its frame of reference. Our intuition about edges and containers is a powerful survival tool on Earth, but it is a cosmic illusion. The universe does not behave like any object within it. This is the core of the mystery. We are using a dictionary written for the contents of the room to describe the walls, the architect, and the very idea of roomness itself. The question feels urgent and sensible because it is built from the grammar of our everyday experience. Yet the answer, as best as we can articulate it, seems to dissolve into silence or paradox. Perhaps the most honest scientific response is not an answer, but a recalibration of the question itself. We are not discovering an edge of the cosmos. We are discovering the limits of our own imagination. This cosmic horizon is not just a distance limit, it is a prison for knowledge. We are forever trapped inside a bubble of information, a sphere defined not by walls, but by the finite speed of light and the finite age of the cosmos. Everything we have ever learned, every theory we have ever built about the universe, is based on the light that has managed to reach us from within this bubble. The rest, by the unbreakable laws of physics, is and always will be hidden. It is a humbling truth. We can craft elegant equations, propose breathtaking models of eternal inflation or a multiverse, but we must accept that the ultimate answers to our biggest questions may lie permanently beyond that veil. These theories about what lies beyond our observable universe are not wild guesses. They are often beautiful, mathematically consistent extensions of the physics that work so perfectly inside our bubble. But there is a profound difference between mathematical consistency and empirical truth. We may never receive a signal from another bubble universe, never detect the curvature of a cosmos so vast it appears flat to us, never peer beyond the inflationary epoch that birthed our reality. These ideas might remain forever in the realm of compelling, untestable philosophy. This is the frontier where science meets its own limits. The scientific method is built on observation, measurement, and verification. What do we do when the very nature of reality places the most important evidence permanently out of reach? It forces a kind of intellectual humility. We are like sailors on an ancient ship, mapping the ocean by the stars we can see, while a permanent, impenetrable fog surrounds us on all sides. We can deduce the ocean is vast from the motion of the waves. We can theorize about distant continents based on the driftwood that washes ashore, but we can never sail into that fog to see for ourselves. The mystery of what the universe is expanding into may be one of those eternal questions. It pushes at the boundary of what is knowable, reminding us that the cosmos was not designed for our comprehension. Our minds evolved to navigate a world of medium-sized objects moving at slow speeds, not to intuitively grasp the birth of spacetime or the meaning of infinity. So we build tools, both telescopes and mathematics, to extend our senses. We piece together a story from the faint whispers of ancient light and the subtle behavior of distant stars. That story is magnificent and growing, but it may always have chapters we can read only in theory, never in fact. This is not a failure of science, it is a revelation about the universe itself. Some truths are structured to be forever just over the horizon, not because they are unimportant, but because the cosmos is simply that much grander than the perspective from our tiny, luminous point within it. Our struggle to comprehend the cosmos is not new. For as long as we have looked up at the stars, humanity has told stories to frame the unfathomable. Long before telescopes and equations, every culture crafted its own cosmology, a narrative to explain where the world came from and what, if anything, lies beyond it. These ancient myths reveal a universal human impulse to find boundaries in the boundless. The Hindu scriptures, for instance, describe a universe that endlessly cycles through creation, preservation, and dissolution. Each cosmic cycle lasts for billions of years, only to begin again, a concept that echoes the modern scientific speculation of a cyclic multiverse. In ancient China, philosophers pondered the idea of the cosmic egg, from which the ordered world hatched from a formless chaos. Norse mythology envisioned a great world tree, Yggdrasil, whose branches and roots held the 9 realms, existing within a void called Ginnungagap. Perhaps most famously, the question of what supports the earth led to the image of a world resting on the back of a giant turtle. And what does the turtle stand on? Another turtle. It is turtles all the way down. This is more than a whimsical tale. It is a profound philosophical joke about the problem of infinite regress, the unsettling idea that every explanation requires another explanation forever. These stories are early attempts to solve the same puzzle we face today. They instinctively grappled with the need for a foundation, an edge, or a container for reality, often arriving at metaphors of circularity or infinite stacks because the idea of a true nothing was just as troubling then as it is now. This human need to frame the infinite persists in modern philosophy through elegant thought experiments. Imagine a library that contains every possible book that could ever be written. Every coherent novel, every gibberish string of letters, every truth and every falsehood is somewhere on its endless shelves. This is the Library of Babel, a concept by writer Jorge Luis Borges that illustrates the terrifying, sublime nature of infinity. In an infinite universe, is every possible arrangement of matter not just likely but guaranteed to exist somewhere? The philosophical implications are staggering. It suggests that all our questions, including the one about what the universe expands into, might have every possible answer playing out in some distant, unreachable volume of space. Another classic puzzle asks what would happen if you could thrust your hand beyond the edge of the universe. Would it meet a wall? Would it vanish? The paradox highlights how our thinking is bound by the language of objects and actions within space. The question itself assumes you can move in a direction called beyond, which may not exist if the universe is all there is. These philosophical and cultural lenses do not provide scientific answers, but they do something equally important. They show that our cosmic confusion is not a failure of modern physics, but a deep-seated feature of the human condition. We are storytellers and pattern seekers, trying to project the logic of our local world onto a canvas that operates by entirely different rules. By recognizing this, we join a conversation that spans millennia, connecting the mythmaker gazing at a campfire sky to the cosmologist analyzing data from a space telescope. We are all using the tools of our time to sketch maps of a territory that may be fundamentally unmappable. This shared heritage of wonder softens the frustration of not having a simple answer. It transforms the mystery from a problem to be solved into a horizon to be contemplated, a permanent invitation to look outward and inward simultaneously. The distant future of the cosmos may be one of cold stillness, but the immediate future of cosmology is electric with activity. A new generation of instruments is poised to turn our deepest questions into precise measurements, hunting for the subtle fingerprints of dark energy and the primordial tremors of creation itself. On a mountaintop in Chile, the Vera Sea, Rubin Observatory is preparing for a decade-long survey of the entire southern sky. Its enormous mirror and giant camera will not take pretty pictures of individual galaxies. Instead, it will conduct a cosmic census, repeatedly imaging billions of galaxies to track their positions and shapes over time. By watching how the large-scale structure of the universe evolves, and by measuring the subtle warping of light from distant galaxies caused by dark matter, this survey will chart the influence of dark energy with a precision we have never before achieved. It will tell us if dark energy has remained a constant force, or if its strength has changed over the life of the cosmos, a critical clue that could distinguish between a long freeze and a future rip. Joining this effort in space will be the Nancy Grace Roman Space Telescope. With a field of view 100 times larger than the Hubble Space Telescope, Roman will perform its own vast surveys, peering back to when the universe was only about 2 billion years old. It will discover thousands of new exoplanets and study the atmospheres of distant worlds, but its primary cosmic mission is to trace the expansion history of the universe with exquisite detail. By finding and measuring distant supernova and mapping the distribution of galaxies in 3 dimensions, it will create a movie of cosmic expansion, frame by frame across billions of years. Together, these observatories will not just collect data, They will test the very foundations of our models, potentially revealing if Einstein's cosmological constant is truly constant, or if a more dynamic, unknown force is at work. Beyond mapping the effects of dark energy, the ultimate dream is to witness the moment of cosmic birth directly. For that, we must listen rather than look. The theory of inflation predicts that the violent expansion of the infant universe would have sent powerful ripples through the fabric of spacetime itself, primordial gravitational waves. These waves, unlike light, would have traveled unimpeded through the hot, dense plasma of the early cosmos, carrying a pristine signal from the first fraction of a second. Detecting them would be the smoking gun for inflation. While we have observed gravitational waves from black hole collisions, these cosmic signals are far older and fainter, imprinting a unique swirling pattern on the polarization of the cosmic microwave background. Ground-based telescopes at the South Pole and in the Chilean high desert are scanning the ancient light for this faint curl pattern with increasing sensitivity. Future space-based observatories are being designed with this singular goal in mind. Finding these waves would not only confirm inflation but potentially tell us the energy scale at which it happened, opening a window into physics at energies 1 trillion times higher than any particle collider on Earth could ever reach. The ultimate answer to what the universe expands into may forever hover at the edge of comprehension, a mystery woven into the architecture of reality itself. Yet this is not a cause for despair, but a source of endless inspiration. Each new telescope, each more sensitive detector, refines our questions. We are not circling closer to a final, simple answer. We are mapping the vast and beautiful landscape of our own ignorance, discovering that with every horizon we reach, a new and more wondrous one appears. The journey of understanding is itself the destination, a perpetual expedition into the grandest mystery there is. We are left then at the edge of understanding. After this journey from the first redshift to the accelerating horizon, what can we honestly say we know? Our current best guess, the synthesis of a century of observation, is both elegant and deeply strange. The universe expands because the fabric of spacetime itself is stretching everywhere at once, powered by the enigmatic pressure of dark energy. The geometry of this fabric, as measured in the ancient light, appears flat. This points toward a cosmos that is likely infinite, with no edge and no center. If that is true, then the most scientifically grounded answer to our original question is a quiet revolution in perspective. The universe is not expanding into anything because the concept of an outside has no meaning within the framework of everything. The question is a beautiful trap built from the language of objects within a container, trying to describe the container itself. We have been asking a question that, in its most literal form, might be as nonsensical as asking for the smell of a triangle, yet the human mind rebels against that answer. It feels like a surrender, so science, in its boldest speculative forms, offers alternatives that stretch the imagination even further. Perhaps our universe is one bubble in an eternal, inflating multiverse, expanding into a grander arena we cannot perceive. Or maybe we exist on a three-dimensional membrane drifting through a higher dimensional bulk, giving the expansion a literal direction we can never point to. These are not just fantasies, they are mathematically consistent extensions of our most successful theories like inflation and string theory. They provide a kind of answer, but at a cost. They push the ultimate mystery one step further away into realms that are, for now, permanently beyond our observation. So where does this leave us? With a profound and humbling admission, the true, complete answer to what the universe is expanding into remains one of cosmology's deepest enigmas. It sits at the precipice where our hard-won data meets the limits of our intuition, where the map of known physics fades into the terra incognita of ultimate origins. This is not a failure. It is the signature of a universe grand enough to forever hold mysteries in reserve, a constant reminder that the cosmos was not designed for easy comprehension. The search for the answer has given us something perhaps more valuable, a breathtaking story of discovery from a static sky to a dynamic, accelerating expanse, a narrative that continues to unfold with every new telescope pointed at the dark. From the startling redshift of distant galaxies to the invisible push of dark energy, this has been a journey across the very fabric of reality. We followed Edwin Hubble's revelation that space itself is stretching, an idea best captured by dots on an inflating balloon. We wrestled with the mind-bending notion that this expansion might have no outside, no edge, and no center. We met the mysterious force of dark energy, now accelerating that stretch toward a cold, distant future. And we ventured into speculative realms where our cosmos might be one bubble in an eternal multiverse, or a holographic projection from a distant boundary. Each step challenged our deepest intuitions, forcing us to abandon the idea of the universe as an object in a container and see it as the container itself. So where does that leave our original, haunting question? The most profound answer modern cosmology offers is also the simplest to state and the hardest to truly feel. The universe may not be expanding into anything at all. There is no into. When we say everything is expanding, we mean that the definition of everything is dynamically, relentlessly growing. The distances between the threads of the cosmic tapestry are increasing, weaving more emptiness, more potential, more room for existence between all points. Perhaps the universe isn't rushing into a void. Perhaps everything is simply becoming more everything. It is a concept that stretches the mind as surely as dark energy stretches the cosmos. This mystery lies at the beautiful frontier where our knowledge meets the unknowable. What do you think lies beyond our cosmic horizon? Share your own theories and questions in the comments below. If exploring these edges of understanding sparked your curiosity, subscribe for more journeys into the deepest mysteries of space. Thank you for venturing this far.